Well, good afternoon, everybody. Dan Hay-Bison with Grace Engineered Products. I'd like to welcome you to our webinar this afternoon. Joining us is John Kolak, a certified safety professional, and today's topic is going to be NFPA 70E, how safety by design leads to safer and more productive lockout tagout. So as we begin, as we go through this process this afternoon, we're going to reach out with some polling questions to you and ask for your input along the way. Also, if you have any questions, go ahead and feel free to type them in, and then at the end of the seminar, we'll be going through each of the questions as time permits and be responding to the whole group. And when we do, we'll read the question and then respond. That being said, I'd like to welcome John Kolak this afternoon. He'll be our first speaker. John?
Thanks, Dan. Good afternoon, everyone. Thank you for tuning in. Hopefully we'll be able to give you some useful and practical insight into both safety by design and insight into electrical lockout tagout in particular. Let me give you a little bit of my background so you have a frame of reference where I'm coming from, and then we'll sort of introduce the general subject matter for the presentation, and then we'll jump in with both feet. In terms of my background, I actually started out in the electrical world as a lineman. I'm a journeyman lineman from the IBEW. I climbed poles for a number of years before going back to school. I took education and bachelor's degree in electrical engineering and a master's degree in occupational safety. And as Dan said, I'm a certified safety professional. My role in the webinar will really be covering more of the regulatory engineering and safety side of the discussion. Dan will be talking to you more specifically about safety by design and particularly with respect to the use of permanent electrical safety devices, PESDs, and how they fit into the safety by design model, if you will. And with that said, let me just lay a little bit of groundwork about some of the terms and things like that we're going to be using in the presentation. The term lockout, tagout, and energy control are synonymous. The OSHA standards and all that we're going to be talking about are called energy control. With that said, we all refer to it as lockout, tagout, so that will be something to keep in mind as we go through and as you read the slides. Also, there are three terms that are synonymous with each other, that being the term zero energy state, an electrically safe work condition. You may recognize that from Article 120 in the NFPA 70E, and the word dead. Those are all synonymous terms. So we want to be careful, for example, to only use the word dead when we really mean dead, and we'll talk about how to get to that dead or a zero energy state as part of the presentation. So in terms of what we're going to cover, we're going to talk about the differences between lockout, tagout, and the OSHA standards versus the NFPA 70E. There are some differences that we want to cover, and of course how OSHA would normally have you manage any hazard would be to follow whatever standard provides the most restrictive protections. So in some cases the 70E has additional precautions that OSHA does not, and the reverse is also true. OSHA occasionally has some things that are not in the 70E. With that said, when you're applying the standards, always know both standards or all the standards that might apply and then follow the most restrictive of them. We're going to talk about some of the energy control and lockout tagout challenges that exist. Some of those challenges are in the form of the configuration of the equipment or the type of equipment. Some equipment is not lockable by its design due to its age or something else coming from a foreign country. We'll talk about some of the challenges that you might face, and in particular some axioms that you can use to follow and to protect yourself in those situations where the standard issue lockout tagout wouldn't apply. We'll talk about some of the hazards associated that can happen while you're in the lockout, tagout, or energy control process. Again, that can involve both shock hazards and arc flash hazards. And this is also one of the times where the use of PESDs is particularly useful. And so Dan will be talking about that later especially. And then we will be talking about electrical lockout as opposed to mechanical lockout, tagout, which you'll see in the reference there, 29 CFR 1910-147. That actually is the OSHA lockout or tagout, or if you will, energy control standard. So we'll be talking about that because that's one of the key things to get from the presentation is the difference between electrical lockout and every other kind of lockout, and also the difference between high voltage and low voltage lockout tagout. Now, when lockout applies, the general rule is that for maintenance activities, it's assumed that virtually all maintenance activities will be done in a lockout, tagged out state. Lockout, tagout, if you think back to the NFPA 70E, those of you that have had that training, while you're in the troubleshooting mode, it's assumed that it's okay to do some troubleshooting or voltage testing in the troubleshooting mode. But once you've identified what the problem is, at that point you're required to lock out, tag out. So generally, all maintenance activities is assumed to be done on equipment that is in the locked out, tagged out state. When production operations are in play, it really applies primarily if you're going to do something like bypass a guard, remove a barrier or something from equipment such that it exposes either electrical hazards or some other hazard as well. And so in the production mode, primarily bypassing guards or putting any part of your body in harm's way would constitute the requirement to do a lockout, tagout. There is an exception for routine or repetitive work when alternative measures are used. I will cover what that would include here in a slide or two, so we'll just park that one for the moment. However, the note at the bottom of the slide is particularly important, and the term equivalent protection exists in OSHA on several levels, but the assumption is if there is a situation where legitimately you cannot follow lockout, tagout as designed, how straight up lockout, tagout, you would be required then to come up with an equivalent system. And the equivalency that we're shooting for is meant to be the protection of actually installing a personal lock or tag as well. So we'll cover the idea of equivalent protection more than once in the presentation. Now, in terms of some basic concepts, one of the primary ones I'd like you to know is called the Two Conscious Act rule. Now, the Two Conscious Act rule doesn't appear in the actual standard itself. It is actually upon which the entire lockout, tagout standards are based. And the Two Conscious Act rule simply says this, that in order to release energy, you're going to need to do two things purposefully or on purpose, and one of those two things must require excessive force. So when you apply this to the idea of lockout, tagout, the general idea would be that in order to have an energy release, you're going to first have to cut my lock off if you were going to energize the circuit I was working on. That is both excessive and purposeful. You're not going to accidentally cut somebody's lock off. And then it's requirement that you do another conscious act, and that would be to reset the device or enclose the device that energizes the circuit. Again, this is all about probability. Dan is going to talk to you a little bit about hazard analysis and risk being a function of both severity and probability. In this case, the logic is that in order to do two things on purpose, it's going to eliminate absent-minded or accidental reclosures, and it's going to require somebody to purposefully do something. And of course, the need to cut off a lock would also preclude anybody from inadvertently doing that. It would be a required purposeful act to do that. So I'm going to mention this because whenever we encounter situations where you can't do lockout, the device will not accept the lock, or it would be unsafe to use that device for switching, I will just refer you to the Two Conscious Act rules. So kind of file that in your mind, and this is also relevant to tagout. If you look at the OSHA standards, when you are not able to lock out, you're going to do tagout, and then the code will say that you're going to do one additional measure equivalent to a lock, and that is really the idea of the Two Conscious Act rules. So if you don't know what else to do on a circuit and it's not lockable by design, go with the Two Conscious Act rule and you'll get compliance by default. The idea of sole control only exists in the OSHA standard itself. It doesn't exist really in the 70E anymore. And sole control simply means that if you have sole control over the energy isolating device, known as an EID, that means you do not need to lock out, tag out that device. So the idea being, of course, if you have control over the device that controls the energy that you're working on, you wouldn't allow somebody to energize or close in on you while you're standing right there. So there's two things to take from that. Number one is what sole control means. The second one would mean that, well, actually I already said that. Let me move on. Now there are three levels of training under the OSHA requirements, under the OSHA standards, and this is really what I would recommend you follow when you're applying and training people on lockout, tagout. The highest level of training is called an authorized employee. Now, an authorized employee, the term authorized really means that they are authorized to use the energy control program on behalf of the company. So in order to be authorized, you are really at the top of the safety food chain, so to speak. meaning that every authorized person must first be qualified as defined in the training requirements for the piece of equipment that they're going to lockout tagout. Then they must take a company-specific lockout tagout training program, which includes about a 4 or 5 hour classroom instruction, a written test for cognitive learning, and then they must go out on the field and demonstrate proficiency on the type of equipment on which they were going to be locking out. And they need to demonstrate that in front of somebody who themselves is an authorized or employee who has been trained as a trainer, if you will, to assess their skill. At the end of all that, they are issued their locks and tags. So an authorized person is very highly trained, very well skilled. So every authorized employee is qualified, but not every qualified person is authorized. So keep in mind what that training requirement is, because the 70E requirements are a lot less clear than that. The term affected simply means what it says. It means some employees that are impacted by lockout tagout, but are themselves not allowed or trained to affix lockout tagout and control energy. An example of that would be a machine operator. If we lock out their machine, it certainly impacts their ability to function, but they actually are doing nothing with respect to energy control themselves. And of course, the category other is a catch-all. Anybody who doesn't fit in the first two categories would be in the third category called other. And the training for affected and other is really just a very brief safety meeting, a 15 or 20-minute safety meeting, whereas authorized training would take the better part of the day to complete. What you see on this slide is actually a snip of the OSHA training, the NFPA 70E requirements, training requirements as it relates to lockout tagout. Now again, as you read this, it's very lightweight, not very clear, and keep in mind that the lockout tagout requirements are what we call very broad-based standards. In other words, lockout applies to everybody from a small electrical contracting group all the way to somebody like General Motors. So because of that, you're going to find the lockout requirements are very generically written. They don't give you a lot of precise specificity. And it is Dan and my job to give you some specifics as we work through this in terms of electrical equipment. So again, if you have questions after we cover a topic, please type those in and we'll be sure to answer those questions at the end. So the training requirements, as you see here, are pretty basic under 70E. Of course, the qualified electrical requirements, both in OSHA and the 70E, also reference energy control. So this isn't all they have to say about it, but suffice it to say that I would recommend you follow the OSHA requirements because they are a bit more restrictive and a bit more clear and easy to understand. Now let's talk about the difference between electrical lockout and mechanical or any other type of lockout, and we'll also talk about the difference between high voltage and low voltage lockout. Now, in this example that you see in the picture, we have an energy isolating device. And again, the term energy isolating device is critically important in lockout because only energy isolating devices can be locked out. You cannot lock out tagout controlling devices like push buttons or toggle switches or safety switches, things like that, emergency stop circuits. You can only lock out tagout and EID. So in this case, we actually have a insulated case circuit breaker, an ABB breaker, that in this example is feeding an electrical motor. And through a separate shaft, this motor feeds a mechanical pump. Now, in the definition of lockout tagout actually appears at the bottom of the slide. And it says that electrical lockout tagout exists when the nature of the job will require the worker to touch normally energized parts. So we're not talking about systems that become inadvertently energized. If it's designed to be energized and you're going to touch that with any part of your body, you are going to need to use electrical lockout. If that is not the case, as would be, for example, in the situation where we were changing out the pump. In my example here, the pump is driven by a mechanical shaft. There are no electrical parts in it. Straight up 1910-147 would be applicable. On the other hand, if we were going to change that motor out, you see the cover there on the T leads on the motor. If we were to remove that cover to do the voltage checks we would need to do, well, of course, that would require electrical lockout. So that's one thing to know, is the difference between electrical and mechanical. Now, with respect to low voltage lockout tagout on that motor, there is an additional requirement to the mechanical lockout requirements for voltage tests if we're going to touch that motor, change that motor out and touch those T leads. We'll cover that, and there are two additional requirements when we get to high voltage requirements. And the words high voltage are going to be referring to 601 volts and above. Systems 600 volts and below are really considered low voltage equipment, and the low voltage requirements would apply, which we're going to cover here in the next slide. So from this slide, just understand the electrical lockout versus mechanical, and understand that there's a difference between low voltage and high voltage lockout, and we're going to cover that right now. Now, under the left column, we have straight up mechanical lockout tagout. And so let me just walk you through these steps because they're going to be repeated in the next two systems. For straight mechanical lockout tagout, assuming that we've already bled off any stored energy, things like that, the first thing we're going to be doing is opening the energy isolating device itself. We're going to affix locks and tags to that device. Step 3 in my outline is an additional step that is not required under OSHA or the 70E. It is something I recommend you do, which is to try to close the device in with the energy isolating device locked out. There's a remote possibility that you'll be able to do that with the locks and tags on there, and it's important that you know that. Then, of course, we'll do the try test. We're going to try and start the device. Hopefully, the device will not start. If the device does not start, you return it to the off position, and at that point, according to 147, you're able to go to work. Now, if we're going to change that to changing out that motor, the first 4 steps are the same ones we just covered on this previous slide, on the previous column. You're going to do the same thing as you would do for mechanical lockout. At low voltage, 600 volts and below, there's only one more requirement, and that is that you do a 3-point test with a sensitive voltage testing device. And you can see they want you to test face to ground and face to face. Now, this often can be done with a voltmeter or in some cases a proximity tester. But this is really where the PESDs stand out because you don't have to get involved with interfacing with the energized parts, and you have a barrier between you and those energized parts, and also obviously protects against arc flash hazards. But I'll leave that to Dan to talk about that a little bit further. So on low voltage systems, the only requirement in addition to mechanical lockout would be a 3-point test with a sensitive voltage testing device. So this is sometimes known as known, unknown, known, live, dead, live, and dead is a misnomer there. You're not dead until you do that 3rd check. But that's the 3-point test is the only difference between mechanical and low voltage lockout. Now, if we make the move to high voltage systems, say for example your 2400 volt motor starters, there are additionally 3 requirements, well 2 more in addition to the 3-point test. One is that you must get a visible open in the circuit, a physical break in the circuit itself, like opening up a solid blade disconnect or racking a breaker. And then you must install personal protective grounds. Now, personal protective grounds are not the same thing as a grounding switch or a grounding cart. Those are known as trip grounds, and their intent is to only trip the system offline if the system were to become accidentally re-energized. Personal protective grounds are there to limit voltage across the workman. It's a very technical topic that we could never cover in this presentation. But please understand that above 600 volts, there are only two additional requirements to that 3-point test, and that would be a visible open in the circuit and affixing personal protective grounds on all the phases. Now, lastly on this slide, for those of you that might work on a wind farm or a solar farm, you have low voltage systems that are actually above 600 volts. You may have a 690 volt wind turbine. Some of the solar systems could have as much as 860 volts. They are constructed as low voltage systems, so you're going to use low voltage protective procedures with them. What happened there is the codes that were written long ago were actually intended for 480 volt systems, and they called them class 600 volts primarily to catch 480 and below. So if you are working on a system that's 690 but configured as a low voltage system, you're still going to use the low voltage requirements in that situation. You will not be able to affix personal protective grounds because the system is not designed to accept them. In terms of some challenges, well, there are several. Since January 1st of 1990, everything in the U.S. has to be lockable by design to accept the lockout lock. Of course, now in our global economy, many countries produce electrical equipment that is not lockable. So in those situations, of course, you'd have to use that 2 conscious act rule, right? You'd have to do something equivalent to a lockout system. Sometimes we have unusual configurations of systems. In older times, we used to have high voltage systems and low voltage systems in the same enclosure. There are also situations where some of the equipment is located at the back of an enclosure, which require you to get into an unsafe position to access that equipment. Of course, in those situations, what the 70E calls it is a special precautionary technique would be required. In other words, qualified workers have to be adept at not only doing things by the book, but they also have to know what to do when it won't fit normal by the book requirements. Old equipment, well, you can see on the right a picture, one of my favorite pictures of the hydroelectric plant that is still in operation today. What you see there is about a 102-year-old rheostat for a hydro plant, still working 102 years later. Of course, energy control on these sorts of things would require special techniques. However, I think it's fabulous that anything can be constructed and run for 100 years. I'm pretty certain nothing we engineer this year will still be working in the year 2017. So hats off to those people who did that. But of course, it would require special precautionary techniques. Some equipment is malfunctioning, especially with respect to single-phasing breakers, meaning one or two poles of a three-pole device do not open up when the device opens. In these situations, your ammeter would be a very useful device. If it happens to have an ammeter associated with it, you'd want to use that ammeter to read current flow in all three phases. When the breaker opens, you'd see the current flow go to zero in all three phases, and that would be an indication that all three poles open up. However, the PESDs will give you some indication of that because there'll be potential there, which again is a useful attribute of those systems. And then, of course, damaged equipment. Some equipment will be damaged to the point where it would be unsafe to use it for isolation of circuitry. One good example of this is that molded case and insulated case circuit breakers are actually rated for only a single close into a short circuit. So if you reset a breaker into a dead short, you've actually used up the design life of that breaker, and it would not be a recommended procedure to use it again until that device has been tested and recertified or rebuilt. With that said, that's one of the more common things that happens in industry. Trial closes are common. They stress the electrical system, and they are beyond the design life of the breaker itself. Last but not least, some concerns during lockout tagout. Well, stored energy is always a potential challenge. At the top of the list is really capacitors. They are by design, they store electrical charges. So some capacitors have a grounding reactor or a grounding resistor with them that will bleed the voltage down on the device in 5 minutes or so. Others do not. But capacitors always represent a possible source, and they have to be isolated if you're going to do lockout tagout. Of course, batteries are the very definition of stored energy. That's the point of the battery bank. And they represent hazards both in terms of shock hazards. They also represent arc flash hazards, and they represent explosion hazards, especially if they're vented. Vented batteries often off-gas hydrogen, which is very explosive. Shielded cables are a very definite electrical hazard that must be taken into account because of stored energy. And by shielded, we mean that there is a metal jacket of some kind around the outside of the conductor. In most cases, on high voltage systems, this will occur above 5,000 volt systems. Historically are required to use shielded cable. That is going to change in the code to 2,500 volt systems. So even your 4160 motor starters may very well have shielded cables on them in the future. But suffice it to say that most of the time you have a concentric neutral around the device, on the cable. Concentric meaning in a circle, and it is a neutral because if you actually added up those strands, they are sized as a neutral for the phase conductor. When there is a shield around the outside of it, it acts in every respect like a capacitor, and it can store a charge that can be fatal. Variable frequency drives also often have capacitors or other storage devices in them that can backfeed or, release energy, and those also need to be isolated if you're going to be working on those pieces of equipment. Misidentification of circuit components can be a very significant problem, especially with respect to identifying what is line side and what is load side. Please do not assume that devices are top fed all the time. There are many situations, and a wind turbine is one, where you may find breakers that are bottom fed. So make sure that when you're doing your testing or when you're installing a device like a PESD, that you're clear on what is the source and what is the load side, and it may not be the top set of contact points. Sneak circuits can exist anytime there's a junction box. Basically, a significant remodel where additional walls have been added, for example, could be a problem. But we have a circuit that comes from a source that we didn't know was there. So sneak circuits represent a problem, especially when you do remodels inside of buildings. The idea of energy isolating devices versus controllers is also very important. In the picture you see on the right, you see a selector switch that is lockable, and the key part of that is a selector switch is not an energy isolating device. It is a controlling device, and it would not be legal to lock that out with a lockout lock. If you were going to lock it out, use something other than a lockout lock, the appropriate energy isolating device would be actually the circuit breaker that feeds that entire panel. Locking out this particular controller, there might be 2 or 3 other possible ways for that device to become energized. So you cannot lock out, tag out controlling devices, push buttons, toggle switches, selector switches, emergency stop circuits, etc. You will not be legal to lock those out. You're going to lock out only energy isolating devices, also known as source devices. And we've already covered alternate feeds under the sneak circuits, but do suffice it to say that transfer switches and alternate generating sources are sources of potential alternate feeds. For those of you that do work on high voltage systems, station power transformers and potential transformers used for metering and relaying also represent alternate feeds that need to be isolated. So with that, I'm going to hand it over to Dan, and he'll talk to you about safer by design.
Well, thanks, John. I appreciate that. And as I'm switching over here, let me bring up this presentation. But I just wanted to go back and touch real quickly on what you just said regarding the wind turbine, where it's actually fed from the bottom and not the top. That is amazing. It's one of those things that people don't think about, but it only makes perfect sense. And you obviously have to know what you have to be trained and knowledgeable of your equipment and interact with it. So that's a great example of the urgency and the need to make sure that happens. So as we jump into this area, I just wanted to talk about a couple different things, and that is, unfortunately, there are still a lot of electrical injuries taking place. And over a 10-year period from 2003 to 2012, we had about 24,000 reportable injuries, and beyond that, we don't know how many that may not have been reported. But 35% were due to direct contact with wiring, transformers, or other electrical equipment. And probably even more surprising is 60% of these occurred on 3-phase low voltage systems. So going back to what John said, it's less than 600 volts, more commonly even at 480. And unfortunately, testing with a meter is a leading cause of arc flash or incidents, and the costs range dramatically, but anywhere from $50,000 on up. So really what we want to do this afternoon is just talk about some of the best-in-class safety by design opportunities that exist and what that might look like. So as we move forward, one of the things that we really need to be thinking about heavily is the opportunity to do lockout tagout without voltage exposure, and it should be a large part of our panel designs today and our retrofit strategy. So a few things to keep in mind with that is the application of the risk control hierarchy and the opportunities that exist to reduce the risk or eliminate risk in the process. So we're going to go through most of these steps here, and actually, as John had brought up, really risk equals the hazard times the probability of an incident. And when we look at it, moving from left to right on that bar chart, you'll see that the most effective is the elimination of risk. And it's 100% effective, so it's the best practice. By eliminating the risk, there is no incident opportunity and nothing can happen. The next most effective, somewhere under the 100% value, is substituting that risk. And you can substitute in multiple different ways, locking out in different locations or upstream or other opportunities, as well as engineering controls. So reinventing those risks in what they may look like. And what we're going to talk about is some products that really do reinvent that risk and go all the way from that engineering control up and to and through the elimination perspective. On the left-hand side, you'll see those things that are least effective, basically making sure that everyone is aware of the risks. Obviously, it is important that they understand the equipment that they are going to be working on, what the work definition is, and what the potentials are inside. Along with that are the regulatory risks from an administration perspective and what actions need to be taken while they're exposed to the risk. And then the last but not least is the PPE, which is the personal protective equipment that they need to be wearing as their last line of defense. And when we get down to that point, it becomes very personal as to what those devices are. So let me reach out and we'll ask the first poll question at this point. And as we do so, I just want to touch on, the permanent electrical safety devices. And have you ever had a disconnect switch malfunction? And if you would go ahead and provide your response there, we'll get some polling in. At this point, it looks like about 50-50. Actually, 55% say yes, about 37% say no, and about 10 to 12 of you aren't sure, so you don't know. So that's pretty typical, and it is amazing. We recently conducted a study, and we found that 26% of PESD users had experienced some sort of a malfunction in their disconnect. So PESDs help to eliminate and reduce risks, and that is one of the opportunities as we just talked about. So improving mechanical lockout tagout as well as electrical lockout tagout and increasing the productivity and effectiveness of that. In the example there would be, especially in the mechanical lockout tagout, the opportunity exists where you can see that that blade has stuck or that malfunction has taken place. So it also is very good at eliminating risks in creating an electrically safe work condition with a voltmeter, because you can see that not only has the source voltage disappear, but as John also alluded to, is the stored energy is a completely different type of energy that may exist. He had mentioned it may take as long as 5 minutes to dissipate or longer depending on the source. The nice thing about the PESDs, or some of them, is it does bleed down that stored energy. And we'll talk a little bit more about that in just a few slides. But we certainly reduce the likelihood of an arc flash and a shock hazard, and these things, the PESDs identify the voltage sources as required by 70E 120.1 and make sure that you're at the right source. As I go to my next comment, I just want to reach out. How often are you guys doing mechanical lockout tagout in your facilities? And the story I want to share real quickly is a circumstance where I was on site with a customer, and he was actually going through the lockout tagout procedures, and we went to a disconnect location that was away from the actual machine that was going to be worked on, but we started our procedure looking at the machine where there was a voltage indicator installed, and then he went back and through the disconnect and came back out. When we got back out to the piece of equipment, we realized that there was some sort of a situation because the voltage indicator was still flashing. Lo and behold, we had actually turned off the wrong source, and thankfully we were able to see that at the voltage indicator. So it's just one of those circumstances that can happen. Now, as we take a look at the results of the poll, we see about 35% are doing daily mechanical lockout tagout, 24% for weekly, and 42% for monthly. So there is a lot of mechanical lockout tagout going on a daily and weekly basis for sure. So very, very interesting with that. So as we move forward, Don had mentioned about the voltmeter test, or the voltage test instrument that will be used. And this is required by OSHA under 1910.333 and under NFPA 70E 120.15, which is your voltage test instrument. And This is from the time that we hit apprentice school to the time we end our careers as journeymen, that the voltmeter has always been our personal safety device or personal safety tool, because we use it on a regular basis to verify that there is no energy there. Again, going back, John had mentioned it's not required to use a voltmeter for mechanical lockout only when you're going to be working on non-electrical equipment. But it's kind of an interesting change at this point. A lot of applications today don't have the traditional start button on the equipment. They have a start button on the PLC, which makes it a little bit difficult to hit the try button. But you still need to do your bump test or your try test. And we talked earlier about some of the many documented instances where the bump tests identified, or the opportunity existed to identify disconnect failures on different equipment. So I'm not going to really talk a lot about this slide. Just want to point this out. Really, we're talking about two different methodologies here, and one is to be actually inside and exposed to the hazard versus working from the outside of the hazard. So as we move forward, what is the frequency? We've talked about the frequency of your mechanical lockout tagout, but what's the frequency of your electrical lockout tagouts? And we'll push that out. And a lot of you I see are meter carrying journeymen, because you're up at about 46% are doing it on a daily basis, 34 weekly, and about 22 monthly. So that's very good and very interesting. And I'd like to introduce to you at this point the safe test point. And the safe test point is a permanent electrical safety device which incorporates the engineering control portion of the risk control hierarchy and allows qualified or authorized personnel to perform their voltage testing through closed doors. And what we're actually doing here is minimizing the risk of arc flash and shock hazard, because we're mounting these devices at a level which is comfortable to work at and work on, rather than trying to reach above your head under guarding and get these meter tips in where you can to take those measurements. It certainly enhances lockout tagout and productivity, and some of the key features of these devices are the built-in impedance. And really what we're doing here is taking the available energy and reducing it down to a low level. So at 480 volts on a 300 amp feed, the available current at the test points themselves is only 2.9 milliamps of current while we're doing our face-to-face and face-to-ground testing. So there isn't a high potential there as we're going through that process. Like anything, you want to obviously make sure that your voltage test instrument or your voltmeter is rated for the equipment you're going to be testing on. So this device is used to be 0 to 600 AC or 0 to 1000 volts DC. And again, make sure that you're using the proper meter. And these, we get the question periodically, can they be used on different frequencies? And the answer is yes, anywhere between 50 hertz all the way up through 400 hertz. So that's the voltage test point. As we continue on, we're going to add the voltage indicator to this process, and a lot of our customers have told us that this has taken what was just over a 10-minute procedure, reduced it down to basically less than a minute anyway. So as we move forward, I just want to reach out. So how much time does it typically take for you to walk through a lockout tagout procedure? And we're going to give you 4 different options there. As you're responding, we're seeing that most of them are about 54% are 0 to 10 minutes, around 30% are 11 to 20, and 9% 21 to 30. And amazingly enough, with this group, we have about 11% are over 30 minutes to start and finish that lockout tagout procedure. So that being said, we'd like the opportunity to introduced the voltage indicator now, which comes in actually two different varieties of flashing that you see on the screen currently, as well as a solid on. A couple unique things is it's hardwired to the source, and it has a high surge immunity, and you'll see that it's flashing right now. So in a typical system, there is voltage present on L1, L2, and L3, which you see there starting at the 8 o'clock, 10 o'clock, and 2 o'clock position, and no voltage on the ground. If there's a voltage imbalance, the ground would come in and start to flash, or a short circuit somewhere in the system where there is voltage on the ground, it will begin to flash. But if we lose a leg, would be another opportunity where that ground light would come in and start to flash. In this circumstance, as you see, we lost L1 for some reason. It could be a blown fuse or a tripped circuit breaker, or potentially a lost leg coming in from your power company. But you'll see that. And the voltage indicator here is really being used for anybody walking by or an operator to simply look over and see that there's a problem or a change. And really what we're trying to do is to get them to pick up the phone and call the electrical group or the maintenance group. A couple other things. Obviously, these devices are basically UL listed. They are approved to UL 61010-1, Cat 3 and Cat 4 rated, and available in an optical light or fiber optic version for those of you who have strict policies regarding any types of voltage on the door. So what we do is we take that voltage indicator and marry it with the voltage test point, which we had talked about earlier, and we put that under a clear lockable cover so you can see that the voltage is present, keep non-authorized people outside of the equipment, and then only those that are authorized are able to open the equipment and do or perform their lockout tagout procedure. A few minutes ago we talked about the UL listing. So the voltage indicator and the test points are UL listed. When we put it in the housing, it's not complete until it's mounted on your equipment, so it is UL recognized as a complete unit. You can tie it into the line side of the disconnect or the load side or both accordingly. We do have some customers that are utilizing it in both locations. And here's an example of a typical sample procedure. And that would be, again, as we talked about, verify that the test instrument is calibrated and properly rated for the application. If you are using the voltage indicator, verify the test instrument is to a known source to make sure that it is working. Verify that there's illumination on the voltage indicator, and then open the dust cap or the cover, depending on if you're using it with the voltage test station. Insert the instrument probes or the test probes and measure that there's voltage present. Next, you're going to open the energy isolating device, verify that there is no LED illumination on the voltage indicator. The reason that we're going to verify it there first is because that's going to continue to flash until we have bled down all of that energy that may be stored in capacitors in the system. Then we're going to reinsert the test instrument into the probes and measure phase to phase and phase to ground, verifying that there is no voltage. Then we're going to take our voltmeter back to that known source and verify that it is still working. That being said, we're going to continue to follow our facility lockout tagout procedures and do any other steps that are required. And then we're going to do our work, and when it comes time to bring that unit back online, we're going to basically reverse the process, bring the system back up, verify that there is voltage, and see that there is voltage on the voltage indicator. So that's a simple sample procedure. Here's how it all comes together and meets the current standard for NFPA 70E for creating an electrically safe work condition. And you'll see the requirements there on the left-hand side, so from 120.1 all the way up through 120.5, and how the voltage indicator, the voltage test station or test points themselves, along with your current multimeter, meet the requirements for creating an electrically safe work environment. Next, let's talk about, real quickly, we want to send out another poll question. Have you experienced any near-miss situations at your facility? Wow, this is a lot like the first group. So right now we're right around 80% have seen or experienced a near miss, with about 18% have not, and about 6% aren't sure or did not experience that. So you guys know exactly what we're talking about and have seen or heard of that. And that's why it's so critically important that we do try to incorporate any of these engineered controls or safety by design products in your procedures to make sure that that's not happening. At the end of the day, our last line of defense becomes our PPE and our protective clothing and equipment. And after we've tried everything else to reduce the hazards or engineer them out, we've already proven that you know what you're going to be working on and what's going to happen. Now it's the point of putting on your PPE and going ahead and doing the work that you need to do. And, you know, for example, if you're going to be doing some work at height, so obviously you incorporate not only the electrical work that you're doing, but other hazards such as a fall hazard. So you may end up using a man lift, or you may put yourself into a harness so you're secure. And if there is an event of a fall, you're only going to fall a couple of feet rather than, 10 or 20 feet, something like that. But at the end of the day, the PPE should be selected and fitted by the person who's going to use it. They should inspect it prior to its use, and they must be trained on the function and the limitation of each item of the PPE. They need to inspect their gloves on a regular basis and make sure that they're appropriately rated for the equipment. So as we begin to ramp things up, we'll open it up to some further questions, but as we do, just realize there are further opportunities coming. So electrical safety is much different than it was, 80 years ago, where the electrician handbook actually said a lot of men could test the voltage with the back of their fingers without severe pain, to all the way where we're at today, where we're doing it through voltage test stations with voltmeters, and the potential current is non-existent at 2.9 milliamps. So the evolution in electrical safety continues. Some other areas that you're starting to see a lot more growth and evolution is in switchgear monitoring regarding temperatures and bus voltages and currents and so forth, communications up to SCADA systems for remote monitoring, remote racking products, as well as portable disconnect operations that allow you to be remote while you're actually throwing those disconnects. And we see over the next several years that there's going to be a lot more evolution coming. That being said, we are at the end of our presentation. We'll put up some information. If you have any questions, you can send those through now. We'll take a look. We'll also push out our last poll question to the group and just ask you quite simply, to date, have you installed or are you using permanent electrical safety devices? And that's yes or no. So it looks like a pretty even split. We're about 47% have, with 53 or 57% have not. So it's a nice even split. Boy, it would be great to have you guys being able to communicate with one another, where you could share some stories back and forth. But we have about 10 minutes left, so we have a couple questions. Let me take a look and see what those are. John, I'd like to welcome you back and make sure.
I'm back, and Dan, just be aware, I actually can't see the questions on my palette, so if there's one for me, just narrate it to me.
Okay. What resistor type is used in the voltage test point? Carbon composition, wire wound, or metal film? Man, that's a very good question, and I have to be honest with you, I do not know the answer to that question. I can tell you the value of that resistor and let you know that it is fully potted into test points, but I will take a look and do some research on that and try to get back with you after the end of this event, because as of now, I do not know what type of resistors built in. But I do know, that we do fully pot that unit, so it has high vibration resistance and so forth. So I will reach out to you after this is complete. Richard, your question regarding will you make the slides available for this afterwards? Absolutely. We will put them up on our website, hopefully later this afternoon, if not tomorrow morning, but we can also send it out to you if you'd like. Safe test point and voltage indicator are both compliant with NFPA 70E. Yeah, we had talked about that 2 slides ago at the end, and it showed how these 2 products, along with your voltmeter and your knowledge, can be combined to meet the requirements for a safe lockout tagout process in your facilities. We've got one latecomer. Could the test port with the fiber be used in a medium voltage application to install in a remote mimic panel? So currently, Seth, we don't have a test port for medium voltage equipment. That is an area that we think there are some very good possibilities. We have talked a little bit about that. I wouldn't be surprised if you see something from us in the coming years to address that, but we're not quite there yet, but that is on the horizon. Looks like we have one more. Is the voltage test station part of the NFPA regulation? Again, it's not necessarily part of the regulation, but it allows you to follow all of the steps included in that regulation. John, I don't know if you have any comments there.
No, there's not. The standards will not reference a specific piece of equipment traditionally. They're talking about the attributes of the protective system itself, and that's where the use of the PSD as opposed to something else would fit in. So they won't tell you to use, John Kolak's test station. They'll just tell you these are the attributes of what it is that you need to do in terms of protection. How you achieve that is up to the company using appropriate hazard analysis and other techniques. So it would be inclusive as part of the overall electrical safety program. They won't tell you specifically to use a test point.
John, I think we have one more question for you, and that's from Gerardo. OSHA requirements and NFPA 70E requirements, which ones are more strict? And I know you had alluded to that in an earlier comment. Well,
the answer is it varies. Typically, the OSHA standards were written long ago, and they actually were, the original Subpart S was actually cut and pasted from like the 1990 version of the NFPA 70E at the time. So there was synergy there, but it's evolved and diverged over the years. So on some cases, OSHA is more restrictive, and in some cases, the consensus standards of the 70 are more restrictive. It's not blanket one way or the other on that issue.
Okay, and actually we've got just a few minutes left. There's one more that came in, and this was actually from Rick. It says, why haven't you mentioned the proximity type voltage checkers that allow non-electrical people to do lockout tagout? I know of a few pulp mills here that have them and use several hundreds of these.
Let me have something to say about that one, Dan.
Okay.
I don't ever want to have a non-electrical person using a proximity tester on exposed parts at 50 volts or more. The proximity tester represents an alternative for a qualified worker to use. You're coming way too close to energized parts if you have an unqualified person using a glow stick or a tick tracer. So the glow stick and all of that is just an alternative for somebody who's properly trained. We never want an unqualified person doing that using a voltmeter or something like, or I'm sorry, a proximity tester on the equipment. And that is, again, one of the benefits of the PESD is you're not in proximity to those tests.
Very good. And I know you've used a lot of proximity sensors in your past as far as the high voltage usage.
Sure, and again, it made sense because we couldn't get that close to transmission voltages. But again, they're used by properly trained people, not unqualified people.
Yeah, actually, John, I think this next question too falls right into your bailiwick, and that comes from Hunter. It says, does NFPA 70E training suffice for required lockout training, or should an employer train additionally?
Oh, yeah, no, the NFPA 70E is not even close to what you need for complete lockout protection. It'll refer to lockout tagout, but no, the lockout training program runs around 4 or 5 hours all by itself, and it has to include things like the limitations of tags and appropriate procedures for tagout and all that. So, no, the 70 is referencing the high points. It's kind of like a Cliff Notes version of that, if you will, but formal lockout tagout training includes the hands-on piece as well. So no, it would not at all be complete to just do 70 training.
Actually, there was a follow-up that just came up, John, and I'll throw this back to you too. It says, do you know of anyone or any business who offers lockout tagout training?
Well, sure. Yeah, I mean, most safety professionals, if you look for the Board of Certified Safety Professionals, that'd be a good place to start. But yes, there's many companies that do that, and ours does. There's many companies that do that. So it will not be hard to find lockout tagout training. Electrical lockout tagout training is a bit of a specialty, and if you have high voltage, it's particularly specific. So, but if you're looking for straight up 1910-147, many firms do that.
Exactly, and exactly that, and including yours. So we appreciate that very much. Let's going to conclude. So, do you know anyone in business? No, actually. Are the test points safe to be tested with an amp meter? Actually, they're designed to be used with a voltmeter because we've reduced the available current to such a low value. You need to have that testing done actually with the voltmeter.
Yeah, you need to get an ammeter around the wire itself. It wouldn't make sense to try that on.
Correct. I don't see any other questions coming in, so with that I will thank you for your time this afternoon. If you have any other questions, reach out to either us or John after this event, and we certainly appreciate your time. And until we get together again, stay on the safe side.
Thank you.
Thank you all so much.